Hello everyone, and welcome to this Tobii Pro webinar. Today we will focus on Tobii Pro Lab, our software solution. And I am here with the Tobii Pro Lab team today. And before we start with the presentation, because we will present a bit, I would like to give you a bit of a feedback or a bit of a background information on who we actually are. My name is Milena. I have a PhD in psycholinguistics, where I examined language comprehension in multimodal environments using eye tracking and pupillometry, which means that I actually looked into how following the gaze movements of our interlocutors actually help us understand language better, or more in an easier way, let's say that way. And then I joined Tobii in the sales team as a scientific sales representative, and it has been only recently that I'm now acting as an interim global product manager for Tobii Pro Lab. With me today is Richard, one of the most influential team members, who holds a PhD. Hi, Richard. Holds a PhD in cognitive science, where he studied the interface of language and vision using eye tracking, and later on he focused his research on the methodological aspects of eye tracking studies. And since 2017, he has been a chief product owner in the Tobii Pro team. The newest colleague we have is Marcus, who has Marcus, PhD in psychology from Uppsala. There he studied judgment and decision making, and later on worked in the baby lab doing research in developmental psychology. And this year he has joined the team as the senior, as the scientific product owner. And the last but definitely not the least is Thomas, our engineer in the team, who studied digital signal processing and computer science, and has joined Tobii in 2016, first as a team member in the support and training team, and later on from 2019 has become a very valuable member of the Tobii Pro Lab team. So good work is teamwork. So we are all together here today to present to you Tobii Pro Lab. We will start with a short introduction to what Tobii Pro Lab actually is, which is what I will do. And later on, Marcus will tell you more about infant calibration and what Tobii Pro Lab can offer you to help you calibrate those populations which are not as easy to calibrate using Tobii Pro Lab. Thomas will show you how Tobii Pro Lab can assist you in analyzing your glasses recordings in an easier or less effort, in a way that requires less effort from you. And finally, Richard will try to convince you to start using bin metrics if you're not using them already with your eye tracking studies, and show you how you can do this in Tobii Pro Lab. And finally, we will gather all together at the end to answer all your questions in the Q&A session. So during the presentation, please feel free to use the field for the questions and write down whatever is popping up in your mind as a question that we didn't address during the presentation. All right, so let's get started. I wanted us to be all on the same page of what Tobii Pro Lab actually is, and this is why we're having a little introduction here. So Tobii Pro Lab is an eye tracking software for conducting experimental research. As you probably know, there are also other softwares on the market that can have the same definition, which is why I will try and explain what these words actually mean in the context of Tobii Pro Lab. When we talk about eye tracking in Tobii Pro Lab, what we mean is that this software, together with the Tobii Pro hardware, is actually creating a complete solution that is allowing you to conduct your eye tracking research in an easier and smoother way. So regardless of whether you're using a screen-based eye tracker or a wearable solution, currently in our portfolio we have high-end screen-based eye tracker, Tobii Pro Spectrum. There's a low-end Nano and the middle-range Tobii Pro Fusion. In addition to this, there's the wearable Tobii Pro Glasses 3. Moreover, Tobii Pro Lab supports advanced experiment setups, such as using the screen-based eye tracker without a screen, or using your mobile device, for example, to show the experiment or to conduct your experiment on. When we're talking about what kind of software Tobii Pro Lab is, the first thing that usually comes to mind is that it is very simple to use and there are no coding skills required. And this is something that has been important to us from the very beginning and that we are keeping as a priority, that the adoption time when it comes to using the software is kept as short as possible so that you and your lab members can actually focus on your research and thinking about your research and not waste months to learn the skill of using the software. And in addition to this, we want to support good research practices. These two things might not seem to obviously come hand in hand, but with Tobii Pro Lab they do. This is also why our team is consisting of scientists who know what good research practices are and who make sure that every new feature and future development of the software is actually according to good practices. And so these two things together aim to shorten the time that takes you from your research question to publishable or applicable insights. And when we talk about conducting research, what we usually mean are the three basic phases of any research, and those are the design of your experiment, recording the data, and analyzing it. And this is also reflected in the three modules that we have in the Tobii Pro Lab software. In the design module of the software, you can design the presentation, which will become your experiment, for the screen-based eye trackers. Here you can choose among using text stimulus, images, video, web stimulus, for example, or even screen recording to create the experiment for your participants. And this is also the place where you will define how your calibration will look like. And as I mentioned, Marcus will be there in a bit to explain to you how you can use different features of Tobii Pro Lab to simplify or to make the calibration for more difficult populations easier or more effective. In addition to this, there is the record section of the software where you would choose your screen-based eye tracker. And in addition, you can also choose the participant camera and the microphone. Select your different participant variables and start the recording. So this holds for screen-based eye trackers. If you're using Tobii Pro glasses, you would actually, since these experiments are typically conducted in the wild, so to say, you would actually use a dedicated app, which is called a glasses controller. And then the part of the software which is being used for both wearable and screen-based eye tracker is the analyze part, where you can replay the recording that you have created. In this case, in this example, we have a reading experiment. Here you would also set the events which are important for your experiment, and based on those events, you can create the so-called TOIs as times of interest, those time windows where you want to conduct your analysis. And in addition to this, in this section of the software, you would select also your areas, define your areas of interest, which are those parts of the stimulus that are relevant for your analysis. You can also create the famous or infamous heat maps and different visualizations. And finally, this is the section of the software where you would export your data. You will export the data either in the form of predefined metrics or in the raw format. And one part of this is newly also being able to export your data in the form of pinned metrics, which, as I mentioned, Richard will tell you more about. I would like to mention a few more practical things when it comes to the software before we dig deeper into the interesting parts. And that is that we distinguish among 4 different project types in the software. There is the screen project, which is reserved for screen-based eye tracking experiments. Glasses, which is of course reserved for wearable eye tracking. Scene camera, is there for using screen-based eye trackers without screen. And finally, there is the external presenter project type, in case you want to use another software such as ePrime to design your experiment. So in this case, you would design the experiment in ePrime, but you would actually record and analyze the data into the ProLab. And so considering these 4 project types that we have, we actually distinguish 3 different software editions that you could acquire for your lab. So typically when starting on an eye tracking, you want to have a most controlled experimental setup that you can create. And in this case, you would use a screen-based eye tracker. And if you have only one screen-based eye tracker, then typically you would need just the screen-based edition and not the full edition of the software. So in this case, you can create screen-based screen projects and also scene camera projects. If you're using only wearable eye tracking, then the analyzer edition would be the right for you, where you can only create and analyze glasses projects. And finally, if you're combining in your lab both screen-based and wearable eye tracking, or if you have future ambitions to have both eye tracking kinds, then you would be best suited with the full edition, which would allow you to create all the different project types. If in addition to eye tracking, you want to use other biometric sensors, we have a native integration of Shimmer 3 GSR plus unit. So the analysis of the data of the eye tracking and the GSR would be synchronized directly in the software in Tobii ProLab. And for other biometric sensors, we actually have different partners. And by using our plot format, you would actually record the eye tracking data into the ProLab and do the analysis or preparation for the analysis into the ProLab and export the data in the plot format. This format will allow you to then import the eye tracking data in the partner software and analyze it in a synchronized manner with your EEG or ECG data in the partner software. Right, and finally, the license models. You can use Tobii ProLab either as a subscription if you know that you will have a short-term project and you never want to use eye tracking again after that, which I hope will not be the case. Then you can acquire a subscription for the ProLab, and what will be included there is the upgrade contract for the duration of the subscription. What I would advise you to do, of course, is to buy a perpetual license, which is a license for life. And in this license, you would have included the first year of upgrade contracts and optionally could acquire subsequent years if you wish so. What does an upgrade contract actually mean? This means that you would be able that throughout the year benefit from the different new features that Tobii ProLab gets throughout that year. We have regular releases multiple times per year, and on our website under Tobii ProLab release notes, you can actually see what those releases are. I can tell you that there are a lot of new and very exciting features that are being cooked in the Tobii ProLab currently, and I would love you to be able to benefit from them. So keep an eye on this page and yeah, keep your upgrade contracts running. Right, and now it's time to hear Marcus out and the topic of infant calibration. I have a little disclaimer to make, and that is that we have recorded the other parts of the presentation in order to avoid hiccups when it comes to demonstrating how lab works on multiple screens. And so I will play a video. As you've seen, Marcus is here with us and will be happy to answer all your questions afterwards. So here is the infant calibration.
Hi everyone, my name is Marcus, and in this presentation I will talk about infant calibration and the features that we have in Tobii ProLab to help you conduct infant calibration with good results. So before talking about the features in ProLab, I'd like to start with saying a couple of words about what calibration is and why it's important. So an eye tracker uses a mathematical model in order to calculate gaze point, so calculating where on the screen a participant is looking. And this model, it accounts for individual variation in the shape and the geometry of the eye. And during calibration, the model fine-tunes its parameters in order to achieve a more accurate gaze point. So basically, it takes into account the individual participants' shape and geometry of the eye and uses that information in order to have as accurate as possible of a calculation of the gaze point. So in essence, what calibration does is that it influences the quality of your data. With a more accurate calibration, you will have better data quality. And there's been studies suggesting that as much as 50% of participants recruited in infant studies do not provide data for the final analyses. And there are, of course, many reasons for why this might be the case, but one of them is problems with calibration. So if we can achieve more accurate calibration, we will also have more participants that provide usable data in our studies. So what are some of the challenges when calibrating infants specifically? One of the challenges comes with positioning and movements. So in order to have a good calibration, it's important that the participant is correctly positioned and that it sits relatively still during calibration. And this is, of course, a challenge with an infant that might move around or sit in their parent's lap while we conduct the calibration. Another challenge is that it's very difficult, for obvious reasons, to give instructions to infants. So we might want to have a participant look at a particular place on the screen during calibration, and it's very difficult to tell an infant that it's supposed to look at a specific location. It's also the case that the visual acuity of a young infant is a bit worse than it is for adults or older children. Admittedly, it develops quite quickly during the first year of life, but it's still the case that we need to take this into account during calibration, such that we don't select stimulus that are very small and perhaps not distinguishable by the infant. And finally, and perhaps the biggest challenge for conducting infant calibration comes to attention. Infants have a limited attention span, and this makes it difficult both to keep their attention to specific stimulus targets, but also during the entire stimulus procedure. And this might influence then the quality of the calibration. So what are some of the measures that we can take in order to mitigate these challenges? One thing we can do in order to improve infant calibration is to use an eye tracker with a large track box. So the track box is the volume in 3D space that the eye tracker, in which the eye tracker can capture the eyes of the participant. So of course, if we have more wiggle room, so to speak, where the infant can move a little bit and the eye tracker can still pick up on the eyes, the easier it will be to conduct an infant calibration. We should also seek something where we can have support for correct positioning. So being able to in the software see that we have positioned the infant at the correct distance and that it's positioned within the track box will help us conduct more accurate calibration. And with respect to the challenges of attention, it's important to be able to customize calibration for the specific group that we are running our study on. So for example, the number of calibration points. Might be the case that if we have younger infants, we can only use few calibration points. And if we have a bit older infants, we can use more calibration points. We might want to change the calibration stimulus such that it's attention getting for the specific group that we're testing. And it might also be good for us to be able to toggle on and off validation such that we can make the calibration procedure a bit shorter if needed. And finally, it's also important that we have some kind of procedure or workflow to help keep infants' attention towards the screen during calibration and possibly recalibration. So if calibration on a specific point is not good enough, we might want to recalibrate it, do it again, and then of course we need to be able to keep the attention of the infant towards the screen during this procedure. So let's move over to ProLab and see what features we have in place in ProLab that can help you conduct infant calibration. So now we have moved into ProLab, and I started it up, and I will create a new screen project. And when coming into the project, we will move to Designer. And here you can see that the timeline is already populated with a timeline object, which is the eye tracker calibration. And there's a lot of different customizations that can be done to the eye tracker calibration, and they are available here in the properties panel. And two calibration targets that have been around in ProLab for a long time are the point and video. I will not talk so much about them today, but instead I will show you a new feature that we added recently, which will aid you a lot in infant calibration, and that is the resizing video feature. So with the resizing video, instead of showing individual stimuli for each of the calibration points, we now have the option to show a video which is shown on the entire screen and which animates and resizes to each calibration point when the researcher presses spacebar. So this is a feature that will help you a lot in order to keep infants' attention towards the screen during the entire calibration process. And for this demonstration, I will choose to only show two calibration targets. And you have the option of showing 5 or 9. And this, of course, depends on the age group that you're running and the attention span of that age group. I will also choose here to toggle off validation. So validation is part of the validation procedure. And by turning it off, we shorten the procedure a little bit, which might be good for infants. But of course, if you have an age group that can sit through it, validation gives you extra information about how well your calibration procedure performed. So in the resizing video calibration target, I now have a video here. If it's not available when you open ProLab, you can download the video that we provide for you, or you can add a video from your hard drive that you created yourself. There are two settings for this animation. So we can choose to animate it fast, medium, or slow. Basically, the animation takes half a second, 1.5, or 3 seconds to complete. And this, of course, depends on the age group that you are calibrating and how quickly they can follow the animation. So you will need to try this out during piloting of your study. And we also have a possibility to change the minimum size of the calibration point from 1, 2, and 6 visual degrees. And again, this depends on the age group that you are calibrating. So if you're calibrating very young infants, you might need a larger minimum size than if you're calibrating toddlers or older children. So let's move over to the recorder and see how this resizing video looks when we are calibrating. So now we moved over to the recorder and we are ready to connect a calibration. And one thing that I can really advise you when running infant calibrations and running infants is to have a webcam installed on your system. This makes it possible to add a participant camera to your recording in which you can keep track of your infant during the calibration procedure to see that it's keeping its attention towards the screen and that it's correctly positioned. So please, if you have the possibility, have a participant camera to guide you extra in the calibration procedure. I will remove it here for this demonstration. So in order to conduct a recording, we need to select the participant, and we're now ready to run a calibration procedure. And for this procedure, I have a 2-monitor system set up. And in that case, you will have one moderator screen and one participant screen. I will show you why that makes it a little bit easier to calibrate infants as well. So I will press start recording here. And what you see now is the moderator screen. So on the moderator screen, you get information regarding how the infant is positioned and the distance, of course, to the eye tracker and so forth. But we also have a participant screen, which gives similar information. And this might be useful if you need to go to the infant when it's seated on the parent's lap in order to possibly reposition the eye tracker to make sure that the infant's head is in the track box and that it's seated at the correct distance from the eye tracker. So I will switch back to the moderator screen and I will start calibration now. So in the calibration or in the moderator view now, we have information about, again, how the infant is positioned, also about the points that will be calibrated. And as you can see, my gaze comes back and forth here because I'm looking at 2 screens. But we can also see here that this is the next point that is going to be calibrated, the one down on the right. And it says that if I press space, it will calibrate. So let's move over to see what the participant is seeing. And this is the participant screen. And here you can see that the animation is playing over the entire screen. And this is something completely new. For this demonstration, I've turned off the sound, but if you have sound in your video, it will be played, also help to get infant's attention. So once you have made sure that the infant is looking at the screen, you can press space and the video will resize to the point that is being calibrated and then resize back to full screen mode and keep playing until you press space again. And if we look at the moderator screen, we now see that we have the next point in line to be calibrated indicated so that we know what is going to happen during calibration. The video keeps on playing for the infant, for the participant, and when we press space, it resizes to the next calibration point. And importantly here, now that we have finished the calibration procedure, if we go to the moderator screen, in a short while we can see that the animation keeps on playing. So while you evaluate how well the calibration went, the infant is still seeing the movie on the screen, which of course is helpful if it's the case that you need to recalibrate points. So looking back and forth at different screens here, you can see my calibration was not so good. So here I might want to recalibrate, and I can choose to do that by recalibrating the points that I'm interested in calibrating. And when I feel ready, I can continue, or I can stop the recording here, which I will do. So these were some of the features that we have in place now in ProLab in order to help you with infant calibration. So just to wrap this up, we talked about infant calibration in Tobii ProLab. And as you've seen, infant calibration can be really challenging. In Tobii ProLab, we now provide a range of tools that can help mitigate these potential challenges. And these tools can help improve the quality of data in studies with infants. Thank you.
This was the infant calibration, and now we will move on to the assisted mapping. And Thomas.
All right, hello everyone, my name is Thomas, and I would like to talk to you about assisted mapping and how it can help you analyzing data from wearable eye trackers. So when you're working with wearable eye trackers, things might be a bit more complicated than when you are working with remote eye trackers. So when you're working with remote eye trackers, you have overall a better experimental control. You have a better stimulus presentation control in the sense that you know what you present when you present it. And also you have the same coordinate system for gaze data and the stimulus presentation. Your gaze data is reported on the screen and your stimulus are presented on the screen. So it makes for an easy analysis, or at least easier. When you're using wearable eye trackers, of course you have more natural settings, but then the data is very dynamic. So that can be a bit complicated. Every participant is seeing something different or slightly different. You will have also different coordinate systems for gaze data and the stimulus presentation. So the dynamic data, to try to exemplify that. Here we have 2 frames from a recording made with glasses 3. And you see on the left, I have a frame and I have a stimulus represented in pink here. That is a page from a user manual from IKEA. And that same stimulus in the second frame is actually in a very, very different place when it comes to the coordinate system of the frames, so within that coordinate system. So that's a problem when it comes to analysis. And of course, there are some options to deal with that in this dynamic data. So the first option is to use moving areas of interest. I will explain what this is, or doing manual mapping, or assisted mapping, or a combination of those, of course. So first off, the moving areas of interest. They can be useful in some scenarios. Here, I'm trying to show you what it is. So we are basically drawing an area of interest and using keyframes in the recording to actually place that area of interest. It's not going to match always perfectly with what is in the video here, as you can see, but it can be a first step towards getting some metrics on a specific area of interest or a specific stimulus. So you will get those metrics that you want, but of course, it's a lot of manual work. You will have to do that for every AOI that you have. So you will need to move those vertices, or like those, the vertices of the area of interest for each frame. And then same goes for the recording. Every recording you have, you will have to also go through and do this manual work. So it's a lot of manual work, and we don't really want that. So instead, you could, of course, do manual mapping. So manual mapping, what it tries to do is to actually, in a manual way, you will try to report where the data is in this recording and report it onto a static representation. Here's an image. So if I know that you are looking here, I can see that. I will try to find that spot on the image, click there, and then the data will be associated. And we know that that sample was here. And I can do that for every frame of a movie or the video, or every fixation, for example, inside the recording. So I will do that, find where it is, and click and associate it. So that's what we call manual mapping. It's great because it allows to compute metrics on the AOIs. You will draw those AOIs on the image, on the static representation, and you only need to draw them once. So that's the main thing. You don't need to draw them frame by frame again because you have mapped the data onto the static representation, the snapshots. But still, it's a lot of manual work because you need to go through each recording and do that manual mapping work. So instead, what you might want to do is to use assisted mapping. So it's one step closer to automation of this mapping. So what assisted mapping does is that it uses computer vision, tries to find local features in the video, tries to find some edges in the video, uses some computer vision algorithm to actually find where this specific static representation or snapshots is in the recording of the video. So it tries to find that transformation here, this homography from 2D plane to another 2D plane. And if it finds a match that is convincing enough, it will map or associate this data onto the snapshot for you. So you don't have to do that click anymore. And that's something that can be run over multiple frames, like big chunks of frames, or like video or recordings at a time. And assisted mapping will do that job for you. So what I thought is that I would try to show that to you in Tobii Pro Lab so you get a better idea of what it can look like. So if I open Tobii Pro Lab here, I already have a set of recordings that I've imported in this small project. So there's 3 glasses recordings here, and I have some snapshots that corresponds to my static representations. So if I open a recording here, and I've already run this assisted mapping job on this specific recording, So that's what you were seeing just before. So I have the glasses recording here on the left, and here on the right I have the static representation, my snapshots. I can play them side by side here, so I can see here my participant looking at the manual, and here on the right the representation of the data that I get out of the assistant mapping. It takes a bit of time to run this assistant mapping, so I've done that offline, but the way it works is simple. You just select an interval of your recording that you're interested in, and you can ask Tobii ProLab to run assistant mapping for you. And when you do that, it will add that job in the queue. So you will have a queue of jobs here that are scheduled to run, and give you the result when it's done. So here I have the results of assistant mapping, and you can see that you have some sort of curve here. So this is basically giving you what we call a similarity score. So if I go there, you can see what it is, or similarity threshold. Or like a similarity score. And what this score is basically the algorithm telling us how confident it is with the mapping it's done. So some of the areas here might be looking in red. So these are areas where the similarity value is below this threshold we've set here of 50. So that's 50%, where the algorithm might not be sure 100%. And you can explore those, and you should probably explore those because the algorithm is of course not perfect. You should explore these and try to understand, are they correct or are they wrong? You see that they are marked here with this warning. So you can explore. Let me see if we have some of them that are wrong. For example, that one here was out of the snapshot, so I could actually skip that. And if you find one sample that is wrongly mapped, you can of course correct it manually by just clicking in the snapshot here. And that's the way you would normally do the manual mapping, right? You would just go through an entire recording and then manually map those fixations on the snapshot if you find a correspondence from here. So that's a very quick explanation of what assistant mapping is here. Of course, the advantage I said before is that once you're there and you have mapped all the data onto this snapshot, this static representation, as I mentioned it, then you only need to do this area of interest job once. So you can just draw them once on the snapshot and then right away get metrics out from this. So to summarize, when you're using assistant mapping, there are still a few things that you need to think about. It's not all that easy. So there's the theory and there's the practice. So in theory, this algorithm is optimized for 2D plane to 2D plane mapping. So it tries to find a 2D plane in the glasses recording and maps it onto the 2D plane of the snapshots. So think about the fact that your stimulus should look as flat as possible if you want this to work best. So if you have a very flat area, like in that case, it's quite good. It's a manual, it's a flat page. It will probably work good. Also, it is optimized for feature-rich scenes, and that's the way the algorithm was developed. It's meant to find local features in the snapshots and report it to the recording from the glasses. So in practice, if you have a more visually complex stimulus, it will most likely work better. It uses, in theory, classical computer vision techniques like working with edges, colors, features, etc. So of course, the snapshots that you use, they must be as close as possible to what the participant actually saw in the recording for it to work best. So that's something also to think about. And lastly, I mean, you would think that in theory it works perfectly, but in practice, you still need to review the outputs. It's not always going to work 100%. So it's really good to inspect the data afterwards and see how it behaves. And lastly, I think what is very important, I'll put it in the corner here, is to pilot. So you should try to pilot, try the hypothesis that you have, use the assistant mapping on one or two recordings that you've made in your context or the participant's context, and see how well it works for your case. Right, I hope this was informative, and looking forward to your questions. Thank you.
All right, thank you, Thomas. This was assisted mapping, and we move on to our final topic for today, and those are in metrics.
Hi, I'm Richard Anderson. Let's talk about behavior metrics in Tobii ProLab. Consider you have 4 bar graphs like this, indicating that you spent roughly 30% of the trial looking at a certain target. So now you have 4 identical situations with 4 identical bar graphs. But this is only true if you have aggregated the data across time, so you created an average of the entire trial. If instead of plotting an average across time and across all the trials, you plot an average that is across all the trials, but not over time, that means you would get a certain average proportion for every point in time throughout the trials. So something like this. So in this first case, we have one big hump early in the trial where people tend to look at the target around the 1 second into the trial. There can also be a completely different case where you have 2 humps, so 2 subgroups of trials here that are creating these 2 humps. But they still end up with the same average of 30% of the time looking at the target. And you can also see that, you can also imagine that you have some kind of late effect, that you have the hump in the end instead at the 4-second mark, or that you have 2 late humps because they consist of like 2 subgroups of different trials. And the point here is that all of these 4 situations, they lead to the same proportion in the bar graphs. So by just aggregating over time, we're throwing away valuable information that helps us understand what's actually going on. And this is not something new. So if we look towards other domains like EEG and event-related potentials, you would have curves like this. And then there are distinct components that researchers are interested in, like the P1, N1, P2, and so on. And they have a negative or positive displacement, and they occur at a certain, around a certain time, which makes it relevant to kind of pick out a certain slice of the trial to look for those components. In eye tracking, this is also very well used. I would say most often in a visual paradigm where you plot curves like this, so some kind of average curves across different AOI targets. In this particular case, we have something called something like a target. That's the beaker in this case, and it could have some different competitors. You have some like completely unrelated shapes. They're not interesting at all. And then there is the more interesting competitors. You have a beaker, that's a rhyme because it rhymes with beaker. You have beetle, that's a cohort because it starts with the same initial sounds as the beaker. So beaker and beetle both start with the same B sound. And then you have carrot, which is completely unrelated. And by plotting it over time, researchers noticed something interesting, and that's that, of course, the probability to look at the target, so what is mentioned, if you hear somebody mentions beaker, of course you will look towards it. But as they start to processing it, you see the gaze towards the cohort also rises. And the fact that these 2 curves are aligned, at least in the beginning, has been taken as evidence that we do have some kind of incremental language processing. So we're not waiting for the entire word to be received and then start parsing it, but as soon as we get like the first sounds, just the B, and then we immediately narrow down our choices to the beaker and the beetle, and this is reflected in the gaze. And we have the same thing in other variants of visual paradigms, or more like conversations. So in this example, I'm borrowing from 2 studies that used a variant of a game called Who's There, where you have one director that has a certain array of faces, and the task is for the other person to arrange the faces in a similar order, and they ask questions back and forth to make that happen. In this case, this is a very uncontrolled study, so we can't control what people are saying. So whenever there is some kind of certain verbal onset event, you would trigger some gaze analysis window. So before this event, just to get some kind of baseline of where the gaze is at, and then how the listener or the speaker reacts to a certain statement. So if the listener, in this case the person performing the tasks here, instructed by the director, would ask some kind of clarification question like, has she got blue eyes? And at the onset of that, the researchers were interested in looking at where the gaze of the listener is, if it's towards the playing field or towards the face of the other. And there were also curves like this. So the 0 point here is at the actual onset of the statement. And there was two groups, one with normal hearing children, and one group where there was a hearing impaired partner. And what you see is that you get different types of displacements here. So the group, the pair with the hearing impaired buddy, has a higher gaze towards the other's face. But you may also notice there is other differences in the trial, such as like just a higher level for even for non-requests or non-requests of information. And we could discuss whether the thing happening here before the onset, if that's also reflects something. But just the fact that you're displaying the behavior over time here allows you to generate hypotheses of what is going on. So now I'd like to show you how you would go about doing binned metrics in ProLab, exporting it and plotting curves such as these. Now I have started up Tobii ProLab and I've opened the decision-making sample project, and it's looks something like this. So let's just open a stimuli to see what they look like. So I go to the AY tool, and here you can see what the setup of the trial looks like. So you have a picture of the product in question, you have a nutritional label, and then you have ingredients list and a price. Take it away so you can see it more clearly. And then there's some button for pressing how you respond. And here, if I select this, you will see that these labels here have been tagged. So this one has been tagged with nutrition label, this one has been tagged with picture, this with ingredients, and this with price. And we do that for every different stimulus. We label these AYs like that, because that means we can use this tag as a common handle to get information of all these AYs that share the same status, so to say. Now let's export some metrics. And in here, I have chosen the AOI-based TSV file, so that means I will get one row for every AOI, and now I also enable binning. And this is a small switch here. So I enable that one, and I can modify the binning, the size of each bin that should be created. I've selected 1000 milliseconds, so 1 second per bin for this experiment, because it's normally fairly long trials. People may take considerable time in making the choice. And now here in this metrics list, I can choose what metrics and properties I want to export. So I've selected, now when you have bin metrics, you always get like a column called bin, so that you can't deselect, but you get the bin duration and stimulus variables, AOI tags. That means the tags of the AOIs are also exported, so we know what type of information it is they represent. I've chosen just total duration fixations now to keep it very simple, and then I click export to export it. I have already exported it, so I'm going to open up RStudio instead and reading this file and plot this. So now I've opened up RStudio, which is my front end to using R for processing my data. And let me explain briefly what this script does. So I will use, first of all, to load the data that you just exported. So I'm doing it with this here. And now we can look at the structure. So now it will have one row for every bin per recording per interval in a TOI. So in this case, it's recording 1, participant 1. The time of interest is burger, so this is like a media TOI. So for every exposure here. of this image, you get one interval. So this is the first interval of that type of trial. And this is the first bin, and the bin duration was 1000. And the AOI here is this the buttons, whether you would buy it or you would not buy it. And in the end you have the total duration of the fixations. So it's 0 if there was no fixation. So since every trial has a different length, because it depends on how long time the participants take to respond, the number of bins will not be identical for every participant. That's also why it's good to have a bin duration column, because this means we can see the last bin and how long it actually was, because that affects the metric. So that's a limit to how much of time you can spend looking at something within the bin. So for all the other bins, you can spend 1000 milliseconds looking at the AOI, but in the last bin, since it only lasts 426, because that's it's not evenly divisible with 1000, that was a bin size, you will end up with this kind of small bin at the end. And then it can be good to know and take that into account. That is not as big as a regular bin. So this is basically my data file. And now when I want to plot it, to see what happens over time, I want to first remove these response buttons that I would buy or I would not buy AOIs. I will do that. And then I'm doing some restructuring here. So I first do one grouping to create this one. So now I've summarized the data and aggregated across all the different trials. So I get one average value for every AOI type. So we had these AOI types called ingredients, nutrients list, nutrients label, picture, and price. So, and they looked at a bunch of different products, but for all the projects, we create some kind of average. So in the first bin, they looked at the ingredients on average 17.5 milliseconds. And we get a standard error as well. And now I will continue to do one more summarization again. And this is basically just because I want to, when I'm going to plot it, I need to reduce it down the data even further. And now we can actually do the actual plotting, and that's the last command in this script file here. And then it looks like this. So here you can see on the y-axis we have the total duration of fixations. On the x-axis we have the bin number. What we see here is that people, when the trial starts, people are pretty much already looking in the center, so it's a high likelihood that they're already looking at the picture, so showing the product. But then after that you will see a sharp rise to the nutrition label, and there is also a trend to look at the ingredients. So either you go left and look at the nutrition label or go right and look at the ingredients. And then there's a small hump later. That could be because people who have looked at one of the other. So if you looked at the nutrition label first, you will switch over to the ingredients here. You can see the same kind of hump in the nutrition label. That is one hypothesis. I can't say that that is the case, but that's something to explore further. Whereas you can see that the price is pretty much flat and people don't seem to put that much attention on the price in this particular experiment. All right, now we exported some data from ProLab. All right, now we have exported some data from ProLab and we plotted them over time in R. So let's just summarize and kind of take-home messages. So first of all, aggregating the data across time, for example, take the average across a whole trial, is throwing away information. We see lots of interesting things if we look at the data as it unfolds over time. So even if you don't feel comfortable analyzing such time course data, it can be relevant to just plot it to stimulate new thoughts for the next experiment. But aggregation may still be necessary, so that depends on your statistical skills and the type of analysis you want to do. But at least it should be a conscious decision and you should know what you're throwing away if you do aggregate. So if you want to try and do the same export and plot that I did, then you can find the R script on the link down below. So it's basically on my GitHub page. If you just search Richard Anderson on GitHub, and you will find a folder called Tobii Pro Lab Scripts, and then it's there.
All right. And I wanted to make a disclaimer here that you will also receive the link to Richard's GitHub and to this R script in the email that is following the webinar, and there you also receive the recording of the webinar. And now we can move on to the Q&A session. So I would like to invite Marcus, Thomas, and Richard to join me and show their cameras. And we will be happy to answer any questions that we have received so far. And I would like to encourage you to send any more questions that you might have. So I hope that the audio and the videos have worked well for most of you. I have received a couple of complaints that they couldn't hear and see it well, but I understand that most of you were able to follow well. If not, then in any case, you will receive the recording per email. All right, let's jump into the questions. The first question is for Marcus, I'd say, and that is, how can we change from the mediator screen to experiment screen?
Yes, so thank you for the question. So changing between the moderator screen and the participant screen, but the basic or the short answer to the question is that you would need a two-screen setup. And if you have a two-screen setup, it's possible to show the participant view on one and the moderator view on the other. So.
Yeah, exactly. This shouldn't be a difficult thing to do in the software. All right, let me see other questions. For Thomas, which value is considered good practice for assisted mapping similarity threshold? If you don't have the resources to manually check each record, but want to consider only reliable data for the analysis.
So, I mean, based on what the algorithm does, we know that 70 for the similarity score should be good enough. But again, it's also highly dependent on the stimulus you have, and I said it in the presentation that you need to have that as flat as possible stimulus, so it works best and as representative of what the participants saw. So I think one answer would be to say yes, try with 70, but also try in your own settings and do a little pilot. Look at how it behaves for your stimulus, and then adjust the value accordingly. But 70 is a good value to start with, I believe.
And there is one very related question that just came in that is asking, can we use Tobii Pro Lab in sports environment, and what are the advantages and disadvantages?
So would it be with wearing the glasses? Do you want to answer, Richard? Or?
No, you can go ahead.
Okay. In sports environment, it's possible. Of course, you can use Tobii Pro Lab. It's just that you're going to be limited in what you can do in terms of analysis. It depends a lot on the type of sports you're looking at. Some sports will be easier than other ones. We've had people doing golf, for example, and when you're playing golf on the green, it's very hard to use a manual or assisted mapping. Everything just looks green in the recording, so there's no reference for the algorithm to actually find where to map the data. So you would have to do quite a significant amount of manual work to get your analysis going. In some other settings, I don't know, I might be wrong, but I don't know, if you're playing soccer, for example, trying to shoot a kick I'm always the same position, that might work well. Something to try out because the perspective is kind of good on the goal, so to say. So it's very dependent on the sport you're trying to do. But then this is one thing, is how the analysis works. I think what's more difficult maybe is the hardware and how to handle the hardware when you're actually doing recordings in the field in sports. The fact that you might have a person that is shaking or like moving and making the hardware shake might be a problem. There will probably be issues with sweating. So if it's quite intense, your participant might sweat on the hardware, that might cause other problems. So there are, I think, also some more things to think about when you're trying to do things with sports and do recordings with classes and sports.
Right. I have received also a comment that the presentations have been very inspiring. And I think we're all happy about that. Richard, there's a question for you. How do I know which time windows to select for the analysis in the context of metrics?
Yeah, so the bid metrics, that's about like slicing up the time of interest you decided, but then the question is more like, how do you select the right time of interest to calculate the metrics on? And I would say there's like two uncontroversial approaches and one more controversial one. The two uncontroversial ones are, first of all, to look in the literature. Unless you're doing something completely novel, people have done similar experiments and before, so you know roughly what is the how the case will is expected to unfold. So if you're doing like visual paradigm and you're basically taking somebody else's setup and modifying it a bit, then you can already know what analysis window they used. The other approach that is you should always do anyway is to always pilot, because if you pilot and do a tester experiment with 1 or 2 participants, could be colleagues in the office and don't have to expend real participants, you will see how they behave, and you can see plot the entire trial and see where the curves, where the interesting stuff happens, and then you know, okay, for the real experiment, I will zoom in and cut out my particular analysis window there. And then there is the third alternative, which is more controversial, or controversial perhaps sounds very unethical, but this has been used also, I've seen. And that is to, after you've already recorded the data, you want to select a more tight time window and not analyze the entire trial, because there's maybe lots of uninteresting things. The effect is kind of disappearing in the majority of the trial. And then what you can do, because you don't want to cut depending on, okay, here is condition A and you select there, and here's condition B and you select that. So you want to make some kind of selection that's unbiased towards the different experimental conditions. And in that case, I've seen that people can plot a grand average curve. So take all the data from all the conditions and just plot an average curve. So they will see, okay, here's a curve, here's something interesting happening where things are rising, and then it kind of dies down. So then they cut out the interesting hump and use that. And because they plotted and selected from the grand average curve, they're not biasing the analysis towards either condition A or B if they have 2 conditions. But a warning is that may trigger some questions from reviewers. You will have to argue for that approach as well.
Yeah, it's best to do this for the pilot study.
Yeah.
And then set it in advance. Yeah. Right. Thank you, Richard. All right. Let's have one for Marcus, or another one for Marcus. How to make sure that parents' eyes are not being calibrated or tracked when the child is sitting on their lap?
Yes, so there are multiple approaches to making sure that you're not capturing the parent's eyes throughout the recording. And perhaps the most secure one is to make sure that the parent actually has some kind of cover over their eyes. They might have glasses which are have some black covering or something so they don't see. And that's actually quite a good approach generally, because you don't want the parent, if the child is sitting in the parent's lap, to bias the child by doing anything which is related to seeing something on the screen. And that, of course, will help the eye tracker not to capture the parent's eye. Another approach, if that's not feasible, is to just have the parent close their eyes while you position the child and make sure that it's the child's eyes that you are capturing and tracking before conducting the calibration. So those two, one a little bit less invasive and one more invasive with respect to the parents.
Thank you. Thomas, you said that the video analysis for the assisted mapping is not in real time, but often. How long does it take to analyze a second of movie data with associated eye traces?
So I don't have the exact number in mind, but it's comparable. So if you have about a second of recording, it will take about a second to do the assisted mapping. So it's about comparable to the duration of the recording you have. But I don't have the exact number. But yeah, it's comparable.
All right. Just a second. Is bind mapping possible with audio points too?
I guess that's one for me. Audio points. So I assume that would mean to start to kind of use an analysis window that's defined on audio by audio events. In that case, right now there's no audio events directly in lab. So you would have to set them up manually, because even if there was an audio event, you would still need an event to indicate, for example, where there is a critical word or a critical event in the audio file. That needs to come into lab somehow, and that you would need to manually drop today as a custom event. But once you have that custom event, you can select analysis window. So from this event and then 2 seconds out, for example, and get those analysis windows from all your trials.
Thank you, Richard. For infant intermodal paradigm with 2 stimuli on 2 sides, how to select AOIs? Can we do without the AOIs? I'm not sure I understand the question, Marcus. Shall I repeat it?
Yes, please.
For infant intermodal paradigm with 2 stimuli on 2 sides, how to select AOIs? Can we do without the AOIs?
I would say that it depends, of course, on what it is you want to analyze. So if it's the case that you're interested in the specific stimuli on screen and you want to compare looking time or other metrics towards those specific stimuli, then you will need to create some kind of AOIs around them. In general, when working with infants, it's good to have big AOIs and to have sufficient spacing in between them. That's a good general approach. So I hope that answered the question. Also, yeah.
I can add to that good answer that I think there's one approach. I would say I would still recommend using AOIs, but there is a possibility to not use AOIs. So if it's, for example, if you're primarily interested in the direction of the saccade, so are they looking towards the left or to the right, then you can use a metric called direction of first saccade. So if that's going left or that's going right, you will kind of know or can approximate where they're going to look based on that. The drawback is that you would really need to make sure to capture the first saccade, because if they make some kind of small saccade in the middle of the screen, but they will not move entirely to the AOI, then you will get the saccade pointing in the wrong direction, for example.
Yeah, very good tip. All right. There is one question: what type of machine, which should be related to the assisted mapping? Yeah, but it's not the full question. Maybe Thomas, you want to comment on what kind of machines are advised to?
Yeah. So I mean, we have system recommendations online. You can find them on tobiipro.com in the Tobii Pro Lab products page. But generally speaking, I mean, we're talking more on the recent side, so to say. So i5, i7, you know, within the last 5 years, machine would be what we would recommend. Fair amount of RAM, 16 gigabytes of RAM would do the job. There's no graphic card requirement for assistant mapping. It runs on the CPU, most of the computations. So yeah.
Yeah, thank you. And one more question for Marcus, or in general. If I want to report the results of the calibration in my paper, is there a way to find the data after the recording?
Yes, so there's two ways you can find the data. So first of all, in project overview, you have for each participant the results from the calibration procedure. And also, if you do a data export, you can choose to include both calibration and validation results from the recording. So you have them available when you're doing your analysis, if you want to summarize that and report it in your paper.
Great, thanks a lot. This was the last question that we received. And given the time, I think this is also a point where we could close today's webinar. I would like to thank my team members for joining today and for presenting, and to thank all of you for listening to us today. I hope you hear a lot of informative things and a lot of information that is actually valuable for your research and that you can start using and implementing already tomorrow. So have a nice evening, everyone, and see you soon. Bye.
Thank you.
Thank you. Bye-bye.